So good morning, I am Krishna Kumar from Krishna's Classroom. We continue with another lecture on analysis on Rn. In fact, last time we introduced the concept of derivative. In fact, we looked at the concept of derivative in the light of some problems that you encounter to generalize into higher premises or higher dimensions. Now we continue with that analysis, and if you recall, what we did was the following. You had a function f defined from an interval, an open interval AB of Rn, R1, and to R. This is where we started. Real valued function on the interval AB. And we assume smoothness and all that, but it's not bother about it, like the precise nature of it. Assume that it's sufficiently smooth for the derivative to exist. Then we defined f derivative at x naught equal to limit x tending to x naught of h tending to 0 of f of well defined. There is no problem. This ratio is well defined, where we have h naught equal to 0. Therefore, this ratio is well defined, but the question is whether the limit exists or not. And we found that if the limit exists, then this is called the derivative of f at x naught, and it is denoted by f by x naught and divided by this. Then we found that suppose f is defined from Rn to R or Rn. Then you are talking about a function of n variables for n greater than 1. Then you are talking about a function of n variables. And then if you were to mimic the same thing, so if you write x to be x1, xn, and x naught as x1 naught, something like this, the fixed point on belonging to some omega contained in R. And Rn with all the structure that we have introduced earlier, let's say Euclidean space and so on. And now if you were to mimic the same thing, then you would be encountering this problem. You have x naught plus h minus f of x naught divided by h, where of course h belongs to R. Now there the problem starts. You see that this is of course a vector in Rn, and you are dividing by h and letting h tend to 0. Okay, and then you are asking for this limit if you were to repeat what we did here. But then you find that it does not make any sense to divide a vector in Rn by a vector in Rn. This is not defined at all. So there is a difficulty. So this idea cannot be pushed across. So H, since H belongs to Rn, it does not make sense. About it. This was a problem that we encountered. How to overcome this? This is the problem. Okay? Then, what one could possibly look at is how one works on this idea. Okay. Right. So if you just want the same thing, so what you do is you go back to the one-dimensional case. There you see that this amounts to saying that star stands for f x naught plus h minus f of x naught minus h times f derivative of x naught is of the small order of this means this is equal to some function of h, which is an error in approximating f of x naught plus h minus f of x naught by h times f prime x naught. Okay. Now there is an error term. The error term depends on h and also on x naught. Depends on x naught, but we are keeping x naught fixed, so I am not making some special mention of it. And what you have is this, that is RH divided by norm of h goes to 0, 0. This is another way of formulating it, where you see that there is no division of h involved at all on this term. Okay, completely got rid of that. And therefore, and then you make an observation, because f derivative of x naught is a number. So as we are concerned, it's a number at that stage. And in that case, what is this? See, this number can be written as f derivative of x naught times h, rather than h times f of f prime x naught. Now you see that f prime x naught belongs to is a fixed number. This is determined. Now you see that if you look at this as a map from R to R, okay, so f derivative of x naught defines a linear map on R, defined by A. If you want, you can put x naught here to show that it depends on x naught, it's f dash x naught. Acting over h is equal to f derivative of x naught times h.
Now you recall, in one-dimensional space, linear transformations are characterized by scalars through multiplication. Okay? So every scalar determines a linear transformation. Conversely, every linear transformation is determined by a scalar on R. Now this fact is something that we look at. Therefore, f dash x naught h is now interpreted as a linear transformation or a linear operator. And that of course depends on x naught. It's not the same thing. So this is what you have. Okay? Therefore, how do we push this idea across? Now you see that on Rn, linear transformations are defined. Okay? Therefore, if you can conceive f derivative of x naught as a linear transformation, then possibly we can push this part of the definition across. That means suppose f is from Rn to Rm, okay, and omega is contained in Rn open. And you take x naught belonging to Rn. So we can, you see that f of x naught plus h is a vector in Rn, minus f of x naught is again a vector in Rn, minus a at x naught multiplied acting over the vector h. So what do you need for ax naught? You know that h belongs to Rn. If ax naught belongs to is a linear transformation from Rn to Rm, that means ax naught is an element of the linear space of linear transformations L, Rn, Rm, then a times x naught h belongs to Rn. So you see that this is in Rn, this is in Rn, now this is also in Rm, therefore this expression that you have written here belongs to with this choice. Okay? Right? Now what do you ask for? Formally this is what you would ask for. We would ask for the following: fx naught plus h minus f of x naught minus a this we can accept as some r of h with the property that RH divided by norm of h goes to 0 as h tends to 0. So let us formulate it. So the problem is this: given f from Rn to Rm, f is defined on an open set omega and x naught is in omega Rn. We say that f is differentiable at the point x naught if there exists a linear transformation from Rn to Rm such that f of x naught plus h minus f of x naught minus ah is equal to RH, which is the error that you have, and that is it with the property that RH divided by norm of h goes to 0 as h tends to 0. Now this is the requirement that you ask for, which is amount to saying that norm of RH divided by norm of h goes to 0. They are equivalent. Okay. Right? But the norm that you use on the top will be the norm in Rn. The norm that you use in the denominator is the norm in R. This is the difference that you have. Okay, fine. So we try to define the derivative, and in that case you say a x naught you identify as f derivative x naught, which is in our equations. Okay, so that's a sort of generalization that you can think of. A very natural way in which you go. You see that this our classical definition does not work. Therefore, we reformulate it, and in the reformulation, everything goes to smoothly. Okay, so that can be possibly accepted as a definition of the derivative of f at the point x naught. So now you see that because even in the one-dimensional case, the derivative is manifesting as a linear transformation. So we generalize. Once you realize that, it is quite easy to see how it gets generalized. Now you see that the linear transformation, it manifests itself as a linear transformation from Rn to Rn in the general scenario. Okay, so that's therefore. Okay, so we can now do the definition. So let us work the definition. Let f Rn let x naught belong to omega. We say that differentiable at x equal to x naught if there exists a linear transformation A. If you want, you can use x naught here belonging to L Rn Rn such that f of equal to R of H. This is a term where norm of goes to 0. Or this is equivalent to saying that RH is of the small order of norm of S 0, by which you mean norm of RH divided by norm of H goes to 0. Now just remember that the norm that is appearing on the numerator is the norm in Rn, whereas this is the norm in Rn. Okay, but suddenly it doesn't matter at all. Okay? So this goes to 0. Okay, this is also equivalent to saying that equivalently as norm of f of x naught plus h minus f of x naught minus a x naught h goes to 0 as h tends to 0, or norm of h tending to 0. In that case, we write a x naught to be equal to f derivative at x naught, which belongs to L Rn. This identification should be well understood. That we are now talking about a linear transformation from Rn to Rn as the derivative of the function at x naught. Now we first prove that if the derivative exists, then it is unique. So theorem. In that case, we say that f is differentiable at so we first make certain things clear. If f is differentiable at x equal to x naught, then the derivative is uniquely there exists a unique linear transformation Ax naught such that there exists a unique okay, let's mark this. Let be which implies there exists a linear transformation A belonging to star poles. We claim let A1, A2, that's star holes with A replaced by we show that define B equal to, then this belongs to L. We show that B is equal to 0. Okay. So for that, let us estimate this. BH can be estimated as norm of f of x naught plus h minus f of x naught minus a1h And this, you know, this is less than or equal to A1 H. This is by triangular inequality. Which implies, okay, this is R1H or this is R2H minus R1H. That is norm of is less than or equal to R2H plus R1H, which goes to 0, and these are the error terms that we have. Hence, norm of BH, norm of H is bounded by R2H plus R1H and this goes to 0 as therefore BH now for fixed H not equal to 0, it follows that B of B acting over TH divided by norm of TH goes to 0 as T goes to 0, because as T goes to 0, TH also goes to 0. Okay. Now that means, which implies B H divided by goes to 0 as T tends to 0. And this is possible because H does not, as such, does not depend on T. We have taken H not equal to 0. In fact, what you have is this B of norm of B of tends to 0. So B of a unit vector goes to 0. In fact, this is the choice of H is arbitrary. Therefore, B of every unit vector goes to 0, which in turn means that BH equal to 0. That is A1 equal to. So if the relation star holds with both A1 and A2, then A1 is equal to A2. Or in other words, the derivative, if the function is differentiable at x0, then the derivative is uniquely valuable. F is differentiable at x0, then the derivative is unique. Is uniquely determined. See. So that's a beautiful thing. Remark. F is differentiable at x0, then the right it we designate it you see that in the case n equal to 1, that means functions defined on from as a function of a real variable, single variable, then all these statements hold good. So it's a very legitimate generalization of the concept of derivative from one dimension to higher dimensions. Now remember, this is different from our concept of partial derivative. Now I want to make some remarks on this. The first remark is this, that our star, the expression star, indicates that f of is approximately h. Okay, or you are approximating f of x naught plus h by fx naught plus, that is f of x naught
approximation f of x naught plus f derivative of x naught times h. That is, this is the linear approximation to the function f in the neighborhood of the point x naught. Okay, so this is one an insight into what exactly is going on. So we will go to it and look at this more clearly. So in the one dimension, what it exactly means. The second remark is this. F is continuous at a point at any point x naught where the derivative exists. Okay. So what you have is this. This comes from this f of x naught plus h minus f of x naught equal to f derivative of x naught h plus r h. This is there. Now you see that as h tends to 0, the right hand side goes to 0. Okay. Therefore, as h tends to 0, f of x naught plus h goes to f of x naught. So that follows from that. Okay. So with RH, therefore you see that as and one more thing that you have to observe, this is bounded. Okay, so this goes to 0. Because all linear transformations from Rn to Rn are bounded linear transformations. Okay. As h tends to 0, as h tends to the third remark that you want to do is the derivative of f at x naught belonging to omega is called the total derivative. Or freshly derivative. It's in fact a far more general context you can define this. In fact, in the context of non-linear spaces, one can define this.
So from Rn, you can push this across to even general non-linear spaces which are not necessarily finite dimension. I want to make that remark here because when you do nonlinear analysis, nonlinear functional analysis, you will be working on what are called infinite dimensional spaces, non-linear spaces, and even Banach spaces, where you can talk about functions and then derivatives in this particular sense. In that context, it is called the Frechet derivatives. This is a very limited version that we are talking about. Okay. Now let me do an example. We take A belonging to define now what is the derivative of f? Is f differentiable yes, what is the derivative? Yeah. So we make the following observation. What about f of x plus h minus f of x? This is equal to a of ax, and this is equal to, we have used the linearity because ax plus h can be written as ax plus ah minus ax, and then you get bh. Therefore, you see that f of minus f of x minus ah is equal to 0. This means the relation star holds with for every x. In fact, you have a constant derivative. Okay, this shows that f has a derivative independent of x. This is the therefore, it is you have a constant derivative. The constant derivative is given by the linear transformation A. So, for every linear transformation A belonging to L, Rn, Rm, the function fx equal to Ax is a differentiable function with a constant derivative. The constant being a fixed linear transformation that is appearing in the definition of f. Now we will look at some examples which gives you some insight into this. But I want to make some remarks. Some further remarks is this. The evolution of the concept of derivative. First observed that in the one-dimensional case we had the standard definition where division by h was permitted. Okay, so from the first part was f defined from AB belonging to R that is the first stage where we had the conventional definition division by so we could push the definition across in this case. Now in the case of f defined from omega contained in C, where C is a complex plane. One could do the same thing because you could define f from omega to say C complex functions, and then again conventional definition of derivative given by limit z0 of f of makes sense, and the limiting process was could be justified. So the idea sails through to complex functions of a complex variable without any effort, and you see that the division made sense there because C was a, one observes that division by
was possible because division by complex numbers is very important. That is it's a field. Now this is the see R is a field. So we are talking about subsets of R. Then here C is a field. So you can talk about open sets in C, and there all this division makes sense, and we give you 1 by z minus z naught is a complex number. So that is well defined. So we see that this is the difficulty starts when you go to although C has partly is R2, okay, except for the multiplication of elements that you defined in R2. We don't have any multiplication, okay, but in R2 if you impose a multiplication as in the weird way in which we have defined multiplication for complex numbers, then it becomes a field. And this is the reason why this division makes sense, because given a z0 not equal to, or z minus z0 not equal to 0, 1 upon z minus z0 is well defined as a complex number. Okay, so that's something to be observed. So there was no difficulty to go or mimic the definition from one-dimensional space of R to the space of C. Okay, the division was very difficult. But when you try to do the same thing in on Rn, from functions from Rn to Rn, this was not possible because division by a vector was not different. This was the problem. It didn't make any sense at all. This was a problem. Still, you see that the other directions in which the concepts worked was, if you had F as a map from some interval AB to Rk, that is vector valued functions, then derivative could be defined as f of x naught plus h minus f of divided by h. So if the derivative existed, and if f is given by k, then f derivative, if exists, then is a vector defined by this was very different. There was no problem. Okay, and all these kind of arguments. So once again, we were banking on the field property of R, or here the field property of C. Then of course, okay. Now the next remark is, while dealing with functions of several variables, it was possible to introduce partial variables. For example, for instance, let us take f defined from R cross R to, then f is given by f of x1, or you can even say omega defined in R2 defined from some open set omega table. Say f is given by f of. Now you see that the taking the same paths of definition of derivative, we defined whenever the derivative did exist, define a partial derivative and whenever the limit exists. Defined whenever the limit exists. Okay, these were called the partial derivatives. Okay, now exactly the point was this. See, in the xy plane, suppose this is your omega, you have a point xy, you are taking a derivative with respect to x, means what? You are working on this line. Okay, and you are restricting the function on the line y equal to constant. Okay, this is the line y equal to constant, and we are actually keeping y fixed. You look at this function as a function of x. Now you are in the old ground where whatever you did there can be
done, and that is exactly what we did. We simply ignored y. Okay, that means we kept y as a constant. That means we are on the line y equal to constant. And on this line, we were looking at the variation of x and the rate of change of f on this. Similarly, the partial derivative was, this is again x equal to constant. And on this line, in fact, I think one can make this point as x naught, y naught, and then this is equal to x naught, this is y equal to y naught. And then you are, if you keep y equal to y naught, you get a function of x, and you are talking about the derivative of that with respect to x. And on this line, x equal to x naught, you get a function of y defined, and then you talk about the derivative with respect to y. Okay, so we were defining derivatives along the verticals and the horizontals. Okay, whenever the limit, so that is possible because you are still working with one dimension. Okay, and the division by the increment was well defined. So there was no problem at all. Okay, so this was possible. Since we looked at f along the line and f the y-axis. Therefore, we had the partial derivatives, these were called the partial derivatives, and this idea can be pushed to functions of several variables without any difficulty. Now, treat it along the in the direction of the coordinate axis. Okay, that's what you do. This one dimensional derivative, once again, which is very well defined if the limit exists, because the division by the constants were, or division by the increments were possible in that case. So there was no problem. Now the next stage was, one could immediately extend it. Along curves. Or even more generally in arc. Why is it possible? Just like this. Let f be derived from omega and extend it to axis. There is no problem, but let us look at this. Then we define y equal to, or the function is f is equal to x4 or Z is equal to f of x. So you can take it as a surface social problem. Now we will come to that geometric images later. Now what you do is let x naught, y naught belong to omega. Let x be equal to xt, y be equal to yt, be a parameterized curve in omega such that xt naught equal to x naught, yt naught equal to y naught, and t belongs to some interval t. This is the parameter. So what you have is this. You have a point x naught, y naught. Okay, so you have a curve here. Say this is xt by t, and this is the point x naught, y naught, and we have set xt naught is equal to x naught. So what you have is there is a t interval. This is the t interval. So this is the point t naught. Now t naught is mapped to the point this, and t general t is mapped to this point. Okay. That is xt by t, and this is x naught, xt naught, y t. This is x naught. Now we can talk about the derivative of this function. So what do you have? So f of xt by t is equal to some dt of t belonging to t. That means we are not bothered about f anywhere else except along this curve C, this parameterized curve C. Okay? Right? So now you can define the derivative of f along this curve. That means what you are asking for is whether how f changes as x and y moves along this curve. Okay? So we can now talk about df by dt. Which is equal to d by dt of dt at t. Now this is what you want to find out, and you can define this. This is well defined because you are now the increment comes over here. Okay, you are talking about g t plus t naught plus h minus g t naught divided by h, and limit of that as t tends to t naught. So once again, if the limit exists, so you are asking if
then we say f is differentiable at x naught y naught along the curve it's given. This is possible. Once again, t is a variable. It's a variable, it's a single variable where all your techniques do work. So one could go systematically from derivatives along the lines parallel to the x-axis and the y-axis to more general curves passing through the point x naught, y naught if they were parameterized. Okay, so one could, so in all these cases you see that you have been just working around the idea of dividing by the increment in t in a single variable. There was hardly any problem to execute that. Okay, and from there we made a quantum jump. Okay, the quantum jump that we made was to talk about derivative of a function of several variables or a vector valued function of many variables at some point, okay, which involved division by vectors and which was not possible, and in that case we reinvented the concept of derivative and we get more structurally sound results in the sense that we get a much better perception of what this derivative is. Okay, and that turns out to be what is called a linear transformation from Rn to Rn. Okay, so this in a way I think I have tried to narrate the whole thing going from here, and this is the point where we could go to, and beyond that one required a invention of the concept of derivative or rediscovering what the derivative is to push this across from Rn to Rn. Okay, thank you very much.